Today, our team will bring you an introduction to one of the most advanced science, quantum cryptography. Firstly, let's have a glimpse of the classical cryptography. With the sustenance and the rapid development of computer network technology, network communication, e-commerce, e-finance, and other applications caused an increasing dependence on network in our daily life. A lot of sensitive information transmitted over the network. This requires a good security of the information to keep it away from being theft or being tampered. In this situation, cryptography provides us a strong guarantee. In the way, the main purpose of cryptography is to protect the objects against unauthorized access and secure the channels used for interaction between processes. In detail, messages are transmitted between Alice and Bob. Cryptography ensures that no one else will have access to these messages. To achieve the goals, key crypto system is widely used. In that mechanism, the original message called plaintext is encrypted by using encryption algorithm. Usually, there is a one-way function and a key. Plaintext is transformed to be ciphertext. When receiver receives the ciphertext, decryption algorithm and the key are used to decrypt it back into a plaintext. In this process, someone else without the keys and the algorithms are unable to read the message transmitted. This is how cryptography works to ensure network security. However, reading on the complexity of one-way function and length of encryption key causes potential weakness of classical cryptography. The security of many classical crypto systems is based on the hardness of problems such as integer factoring or the discrete logarithm problem. But since these problems typically are not provably hard, the corresponding crypto systems are potentially insecure. Shannon's theorem, which was proved by Claude Shannon, shows the perfect encryption requires the same length of key compared to the plaintext. This is impractical. Currently, very long keys such as 2048-bit keys are thought to be very safe, as it would take millions of years using the most advanced computers to break through. However, on the other hand, the emergence of a quantum computer caused a significant improvement in ability of computers. In a word, with the increasing availability of modern computers, classical cryptography becomes popular and outdated in the past. But now the milestone of creating quantum computers becomes very attractive. Nevertheless, quantum cryptography becomes a new one. There are two of world-recognized technology, cryptography and quantum mechanics. Difficulty of cryptography is because there are many geniuses. They created complex algorithms and break them. The difficulties of quantum mechanics reflects the magic of nature. The combination of these two sciences will surely make a more amazing one. The first person to write about applying quantum properties as a means of validating physical objects or messages was Stanford Wisner of Columbia University in 1970. Wisner proposed a scheme for using quantum properties to print paper money such that the serial numbers could not be duplicated. Another scheme to combine two ordinary messages into an undecipherable quantum message. His idea was so far ahead of their time that they were not accepted by the publication he submitted. In 1983, this paper was finally published. After other researchers had become interested in quantum encryption, and Wisner's contributions to the field were recognized. In 1984, Carlis Bennett and Gilles Brizard proposed using quantum properties in conjunction with public key cryptography to produce more secure message. This made the first quantum key distribution protocol, called BB84 protocol. And later in 1992, Bennett proposed another protocol called B92. In 1993, BB84 protocol was realized by UK Ministry of Defense studies in QKD. Quantum cryptography attracts the attention of the world and develops very rapidly.
After learning the history of quantum cryptography, let's see why QC theories can work for us. In physics, a quantum is the minimum amount of any physical entity involved in an interaction. The quantum state of a system is determined by positions, velocities, polarizations, spins, and other properties of the particle involved. When taking the quantum world into the computational area, we need to exploit this quantum state to represent the binary digits. So certainly, quantum bits is the analog of classical bits. This can be done using arbitrary attributes from above. One could, for example, use the spin of a particle and let up spin to be 0 and down spin to be 1. Generally, QC makes use of spin properties for photons, polarization, as quantum bits or qubits. Quantum physics can be quite puzzling and often lead to non-intuitive results. This does not mean scientists don't understand the quantum world. On a mathematical level, the models used to describe the mechanics is very successful in predicting the experiment results. Secondly, Heisenberg uncertainty principle. It is said, attempting to measure an elementary particle's position to the highest degree of accuracy leads to an increasing uncertainty in being able to measure the particle's momentum to an equally high degree of accuracy. Based on this principle, in quantum communication, the sending of encoded messages are unhackable by any computer. Because when the messages are carried by tiny particles of light, which called photons, if an eavesdropper attempts to read out the message in transit, they will be discovered by the disturbance the measurement caused to the particles as an inevitable consequence of the HUP. The third is entanglement state. It shows that a physical phenomenon that occurs when pairs or groups of particles are generated or interact in ways such that the quantum state of each particle cannot be described independently. Instead, a quantum state may be given for the system as a whole. Last but not least, non-cloning theory. An arbitrary quantum state cannot be duplicated perfectly. If a measurement allows one to gain information about the state of a quantum system, then in general, the state of this quantum system will be disturbed. Unless we know in advance that the possible states of the original quantum system are orthogonal to each other. It turned out that by using this impossibility smartly, unconditionally secure key distribution could be achieved. Any attempts by the eavesdropper to learn the information encoded quantum mechanically will disturb the quantum state and expose her existence. And also, the non-cloning theory prevents us from using classical error correction techniques on quantum states. By the way, the no-cloning theory does not prevent superluminal communication via quantum entanglement, as cloning is a sufficient condition for such communication, but not a necessary one.
As introduced just now, BB84 is a quantum key distribution scheme developed by Charles Bennett and Gilles Brassard in 1984. It is the first quantum cryptography protocol. Assume the two people who are willing to communicate with each other are Alice and Bob. Alice and Bob first agree on two representations for ones and zeros. One for each, for example, define 1 equals to up, 0 equals to right, 1 equals to up right, 0 equals to up left. Alice sends a sequence of photons to Bob, each photon in a state with polarization corresponding to 1 or 0, but with randomly chosen bases. Bob measures the state of the photons he receives, with each state measured with respect to randomly chosen bases. Alice and Bob communicate via an open channel. For each photon, they reveal which basis was used for encoding and decoding respectively. All photons which has been encoded and decoded with the same basis are kept, but all those where the bases don't agree are discarded. In this scheme, on average, they will discard 50% of the bits sent. The remaining bits could be used as key for encryption. What happens if Eve is hooked up on a quantum channel and measures the photons sent by Alice? Eve has to randomly select bases for her measurement, since she don't know which of the two Alice used at the transmission. Her basis will be wrong in 50% of the time. Whatever basis she chose, she will measure 1 or 0. However, even in those cases where Eve picks the wrong basis, there is 50% chance that she will measure the right value of the bit. For example, Alice sends a photon with state corresponding to 1 in the upright basis. Eve picks up the upright and up-left basis for her measurement, which this time happens to give her 1 as a result, which is correct. As this table shows, on average, Eve will measure 75% of the bits correct. Eve then has to resend all the photons to Bob. By doing so, she will introduce an error. Since Eve don't know the correct basis used by Alice and has to pick her basis randomly, this error will show up as an increased error, which can easily be detected by Bob. Needless to say, the possibility to detect eavesdropping is one of the major advantages with quantum cryptography over conventional cryptography. It is still possible for Eve to eavesdrop just a few photons and hope that this will not increase the error to an army rate. If so, Eve would have at least partial knowledge of the key. Counteractions will be used against this attack. Where Alice and Bob has agreed on the key to use, they need to test for eavesdropping. This is done by randomly selecting a specific number n of bits from the key and compute its error rate, i.e., Alice and Bob compare the n bits over n, possibly open channel, and then discard these bits. If the error rate is below a tolerable error rate, Emax, they can assume no eavesdropping has been done. On the other hand, if the error rate is larger than Emax, someone has monitored their communication, or the channel is unexpectedly noisy. Alice and Bob should then discard the whole key and start over. In practice, for Bob and Alice to compare bits one by one is fairly inefficient, and there are better ways to detect eavesdropping. One method of detection is to take random subsets of the photons received. For example, photons 1, 3, 5, 7, and so on, and add up the quantity of the ones in the sample, also known as a parity check. There has to be either an even or an odd number of ones in the sample. it has been proven that if Alice and Bob's parity number differ, which means eavesdropping has taken place, that there is a 50% probability that any parity check will detect the eavesdropping. It is easy to use a computer to quickly check 30 subsets, which would yield an 1 in 230 chance of not detecting eavesdropping, or about 1 in a million.
However, to make use of quantum cryptography in our daily life, we still have a lot of problems to solve. First, the more efficient mechanism to manufacturing quantum should be built. Of course, on the recipient side, an efficient detector is also needed. And nowadays, QC is applied together with classical cryptography, so the eavesdropping detection is also a problem. Others, according to the self-disadvantages of quantum may become the main bottleneck of applying it. For example, the result will be instability because of photons' activities and the inability to transmit photon while a long distance is also due to its attenuation. In conclusion, we still have a long way to go to realize quantum cryptography. This is all of our presentation. Thanks for your time.